Welcome to another MLOps live stream community. We're really excited today. We're actually taking a little break from large language models. We're going to focus more on computer vision and CV ops and how to scale and work with these models in production. We have a really good lineup today. We're really excited. We're actually just going to jump right into it, but we've got Arno, David, and Fabio here to tell us all about how to handle these things in production, how to scale your CV projects. We're going to jump in really quick, but we're going to let's jump in and we'll handle questions at the end. Please drop your questions in the chat in the live stream. If you do, we'll drop in and ask our speakers those questions as we go. So we'll start with David. David, let me know when you're ready and we'll kick off your talk.
Thanks to the MLOps community for having us, for having me. David Espejo. I work for AI in the engineering team as a developer advocate. I spend most of my time with the Flyte open source community. And I'm here mainly to try to give a brief intro to what the Flyte project is, because it's one of the common patterns here is that both Arno and Fabio are Flyte users. So we thought it would be a good idea to give a brief intro to the project. Cool. We try to look at some of the challenges and hopefully part of the solution or the technical side of the solution here. I've been working for a number of years, mainly on software infrastructure, so not exactly an ML person here, but software infra from Unix mainframes to Kubernetes and mostly everything in between. And I'm a proud father of two. I enjoy running even more than biking, but the picture is me conquering the highest point in my country. I'm based in Colombia. There are a lot of mountains here, and this is the highest point you can get securely on a bike here. So the other day I stumbled upon a really interesting paper. It was published in May this year. And it was interesting because the researchers basically watched dozens and dozens of recordings of this very community of talks from the MLOps community, meetups, and coffee sessions. They annotated, more than 6,000 hours of recordings and then ran statistical analysis to try to find patterns in terms of challenges mentioned throughout the talks. And they came up with a list of 17 common anti-patterns or challenges that MLOps community members find when they're trying to productionize ML products, ML models. And as it turns out, the majority of the challenges are not technical. They have to do with how teams are organized or how the hiring process works for staffing teams and etc. But one of the challenges really stood out for me because on it, the researchers basically depict on one side the data science team or the team that is developing ML models, and in the other side, the ops team. I'm using here a very generic term because part of the challenge another family of challenges were how poorly defined are role names. In the field, we have this very generic ML engineer term, or we have the MLOps engineers, or we have the platform engineers, whatever. So ops team will be here the people or individuals in charge of making sure that the ML models actually are usable and can get into production. But they found this one of the anti-patterns has to do with how expectations differ widely between teams and how it causes tensions or conflicts. Expectations around versioning, code quality, documentation. They mentioned how many times data scientists come straight out from academia. So they have this research-oriented perspective on running experiments and doing all this cool stuff. But in the other hand, we have ops engineers who want to make sure that all this research actually produce something that users or customers can actually use. So we have this divide, and we have different teams with different jargon, different skill sets, tooling, techniques, etc. And it was interesting to me because it reminded me of a seminal book that I read years ago. It was published like 13 years ago from Jess Humble and David Farley. And this book basically set out the fundamental knowledge for an entire new family of practices. Continuous delivery is all about how we take a new idea, be it a new feature, whatever it is, and how do we deliver it to users as quickly as possible. That's the main problem. It's in page 1 of the book. And in the reminder of the book, they basically define a set of principles that developers should use to make sure that they build software that is production grade. And this, in other words, it gave birth to the whole DevOps movement and put into the hands of developers throughout the world the processes, the techniques, the tools, make sure that everyone out there can produce production grade code quickly, and how we can ensure speed and quality at the same time. So one of the core aspects in this book was how they define a set of fundamental principles for software delivery. They are 8 of them. I'm just covering here 4 of them. The first one is create a process that is repeatable and reliable, 2 different things, for releasing software. The other, and yeah, for this process to exist, it needs at least a couple of elements. The first one is you need to make sure that you automate almost everything, and the majority of things can be automated. And the other aspect is that you should keep everything in version control. This is all news for software engineers, right? But probably seems to be still a challenge in ML engineering. The other principle is build quality in. This comes from the lean software development movement. And the core principle here is that the earlier you catch defects, the cheaper they are to fix, right? If you catch a defect or bug at runtime, it's way more expensive to fix that than if you catch it on the development process. Also, this one is very important. I mean, done means released. And the idea behind this is that, and it's related to another of the anti-patterns that the paper mentions, is how there is a general lack of product mindset in how ML ops teams operate, or data science and ops teams operate, because for data scientists, the idea is to produce the most accurate and the best model out there available. But there's a need of a product mindset. We are not just developing the best model out there. We are developing an AI product that should get into the hands of users quickly and keeping high quality. So done doesn't mean that the model is meets some key performance indicators. Done means release. It's right now serving users. And finally, everybody is responsible for the delivery process. It's also a mindset, a culture shift that needs to happen in ML, that it's been happening in software engineering for a number of years. Not only ops or MLOps teams are responsible for the delivery process, but everybody. That sounds good, but probably the techniques, the tooling is not there yet to ensure this. So as dev needs DevOps to make sure that everyone can produce quality products at speed, likewise, ML needs MLOps. And considering this, we need an MLOps platform with some qualities. The first one will be one that enables a repeatable development process. I'm just taking the words from the book. And one of the tactics here will be to version everything, a tool that will help us version every single artifact in the process. Also, a platform that will be reliable in terms of catching errors early. It's a fundamental principle here. And also one that is agile in terms of how flexible and extensible it is. So with this idea in mind, that's how Flyte was born. And if that's all you remember from this talk, I'm happy with that. Because Flyte was born at Lyft back in the days. A team of software engineers saw these challenges and they set out to build their own continuous delivery platform for ML products, like an ML-aware CI/CD system. And that is Flyte, basically. The project was donated to the Linux Foundation early 2021 and became graduate by the end of the same year, which speaks volumes about adoption. And the fundamental idea is that, again, how can we help bridge the gap between model developers and ops teams? And I'm using very generic terms because, as I mentioned, role definitions are still not a standard in the field. So we have in one side, model developers. So the idea here is that for them, the contract should be very clear. I mean, they should have a way to define a model and specify the expected inputs, expected outputs, using type hints in this case, and also the infrastructure requirements, whatever they need from the platform. So if it's the execution of external system, PyTorch, TensorFlow, SageMaker, whatever it is. And in the middle, trying to bridge the gap or doing what a technical tool can do, because the challenge is not only technical. We will have an API that will enforce this contract and will catch errors early on in the process, for example, by doing type checking at compile time, right? And the other part of fulfilling the contract will be to version everything, every artifact in the model development pipeline should be versioned, and also the artifacts there should consume the abstractions, and the system should orchestrate the platform services or infrastructure services requested by model developers. That's the core idea here. Again, the idea is to give familiar interface to model developers and enforce a simple contract with the underlying platform, trying to help with all the challenges mentioned before. Cool. So some elements of the contract, again, trying to dive a little deeper here, is one is type safety. I mean, probably you have more context than myself on how, for example, after doing feature engineering processes, there could be incompatible types between the output of a specific task and the expected input in the next one. So these types of errors are cheaper to fix if they are catched at compile time. That's a core design principle in Flyte. It's a by default behavior. It will not only enforce the definition of types, but will catch incompatible types early on. Also, enabling language independence. The most familiar interface here is Python for sure, and the Python is available from Flyte. But there's also a way to run workflows or tasks written in any other language. Every task is a container in Flyte, and this is a way to kind of abstract away the particular language and use any framework here. And also bringing another of the core principles of cloud native software. I mean, all this moving that is very familiar in software engineering. The iterative definition of the infrastructure of the infrastructure needs. Here again, directly in the task definition, model developers can request whatever they need from the infrastructure, even from an external system, and Flyte will orchestrate interactions with these systems. Right, so that's kind of it. I want to be very brief around this. I will just cover some of the core concepts. Again, every step in your pipeline is a task in Flyte, and every task is a container. As I said, everything is versioned. All task executions are versioned and also strongly typed. So with versioning, you're able to reproduce results of a specific experiment very easily. And also workflows are basically a composition of tasks to achieve more complex logic with different mechanisms. But in practice, you will just use a Python decorator to build a task or a workflow. The launch plan is another instance of how to enforce the contract with launch plans. You can define, for example, default inputs, default arguments for a specific task. You can also define a schedule for a workflow. Also, it's a way to kind of standardize the parameters to run a specific workflow, and also a way to share this with other teams. And finally, projects and domain. This is more related to the GitOps movement, software engineering, how to progress a model throughout different stages until it reaches production, because it doesn't go from development to production in a single step. So these logical groupings are also a core construct in Flyte, and will help you not only organize the process, but enable multi-tenancy and other nice features. Cool. I will leave it there because I know we are short on time. I don't know if there's any question, or we can move to the really interesting talks from Fabio and Arno.
Thanks so much for presenting. I think as people drop their questions with the future talks, I'll jump back in and we'll bring people in to answer them. But yeah, to keep things moving, I think we'll have Fabio come on next and talk about some really great stuff. Thanks so much, David. And Fabio, I think whenever you're ready, maybe a quick intro, and then you could jump into it.
Yeah, thanks for introducing me. My name is Fabio. I work as a software engineer in the MLOps team at Recogni. I'm also a member of the technical steering committee of Flyte. Before that, I built up the MLOps team at another company and also worked as an ML engineer there. Originally, my background is in astrophysics, and I'm based in Berlin, in Germany. Today, I'll talk a bit about what we do at Recogni, and then in particular, how we in the ops team work together with the ML teams to together quickly prototype and experiment using our developer platform that leverages Flyte, and then I'll talk about some really cool Flyte features that we make a lot of use of on our developer platform. So about Recogni. We produce neural network inference systems for automotive driving and autonomous mobility applications. Our inference system has a lot of compute, very low power requirements, and low latency. For example, on a common benchmark called MLPerf SSD large object detection, where you do 2D object detection on an input resolution of 1200 times 1200 pixels. Our system runs at roughly 300 frames per second and really low wattage of, I think, like 5 watts or so. We make that happen by using a patented logarithmic number system. I'll talk a bit about how that works in a second. We're co-based in San Jose in California and in Munich in Germany. Since this is a conference about computer vision, I want to highlight what computer vision engineers do at Recogni. We can broadly categorize that into 3 different things. We develop an in-house perception stack for autonomous driving, covering tasks like simple tasks like classification and driving scenes, but also segmentation, object detection in 2D, 3D, lane line detection in 2D and 3D, etc. Our engineers also perform experiments that inform the development of future generations of our chips. And what we'll talk about today is they develop tooling to mathematically convert and compress models for inference. Why do we need to convert and compress models for inference? The thing is that when models come out of a training pipeline, typically they're over-parameterized and also overly precise. The computations are overly precise because it's typically not a goal to optimize that in a training pipeline. You just want to get the highest performance. But then when you go to inference, you want to get rid of these inefficiencies so that you can run at lower latency or lower power. And on the right here, you see two different videos, segmentation in a driving scene. The top is the predictions in the top are generated with a full precision network, whereas the lower one is running on our chip using a compressed and converted model. The process to do so typically looks like this. You start, actually I'm not in the slideshow, I just noticed. You start on the left with a full precision model, an Onyx graph, and the calibration data set. Then you'll do something that we call post-training quantization with knowledge distillation. I'll talk about what happens in this box in a second, and you get then a model that is compressed and mathematically converted, and then that converted Onyx graph is input to our compiler. You compile the model and you get an executable that you can run on one of our inference systems. So let's talk a little bit about what happens in this box here. As I said before, neural networks, when they come out of a training pipeline, typically have inefficiencies like over-parameterization and doing the computations in an overly precise way, which is not really needed for inference. And this library that we develop in a smart way tries to get rid of these inefficiencies. So we compress the networks and we convert them to a lower precision number system that works in the logarithmic domain instead of the linear domain, basically leveraging the trick that a multiplication in the linear domain is equal to an addition in the logarithmic domain. So a times b can be expressed as 2 to the power of log a plus log b. And additions are cheaper in hardware because they require less area and less power. So by replacing the multiplications in the neural network with additions in the logarithmic domain, we're able to increase latency, reduce latency and power consumption, but increase the compute density. Okay, so that's what we do at Recogni, but what I want to talk about today is how the ML engineers who built this perception stack or this library work together with us in the MLOps team, and how together we quickly prototype and bring new ideas into our libraries. So the goal of one of our teams called Core Tech team, which consists of ML engineers, is to, broadly speaking, optimize the conversion performance of this Recon library. And our goal in the ops team is to provide them with tooling or an internal developer platform that allows them to quickly prototype and perform experiments to determine what changes they want to bring into that library and what changes they don't want to bring into that library. And we want them to be able to do that without having to deal with infrastructure tooling and management and manual management of infrastructure, because that's typically not something that ML engineers are passionate about. So let's consider a scenario where either one of our developers has an idea how to tweak the conversion process in that library, or maybe they read a paper and the paper presents a nice idea how the conversion process can be improved. We want them to quickly be able to run experiments and get an answer to the question whether that change is something that we should include or whether we shouldn't include it. And we explicitly in that moment don't want our developers to have to manually start virtual machines in the cloud, for example, on AWS EC2 or in GCE. Then they SSH into that machine, they create a Conda environment, install requirements, they run some Jupyter notebooks, they write together some summary, they put that in the PR, then this gets merged, but maybe because all of this was manual and a lot of work, they didn't cover certain types of networks, and we merge a change into our library that maybe isn't a good change overall, or maybe only for some types of networks. So we don't want all of these things to happen. We want them to be able to quickly implement the experimental change and then have the infrastructure for that managed automatically. So we automated all of that, partly also using Flyte. I'll show how that works now. So let's imagine that they make a feature branch, they implement the tweak or their experimental change, and then they commit that. And one way to trigger the experiments that we then run to test whether we want to incorporate these changes is to include this command here, run benchmarks into the commit message, and then that triggers a whole range of different things that happen in the background. I took this screenshot here from a really cool article from Google Cloud Architecture Center, where they highlight several different ways that are different reference implementation of how infrastructure for ML can look like at different maturity level of organizations. I can recommend to check this article out. I grayed out some parts here that are relevant for real-time inference endpoints. That's not relevant in our case, so these parts are grayed out. But basically what happens is that our developer implements their experimental change, they commit that, and they trigger benchmark executions to test that experimental change. CI/CD pipelines pick that change up. We build a Docker image using the requirements that were specified, so that we have a reproducible runtime environment. We run unit tests, but then more importantly, we start experiments in our Flyte cluster with conversions of some networks that we use for benchmarking to test how this tweak affects overall conversion performance across a whole range of different networks. And then Flyte tells Kubernetes which resources are needed to perform these experiments. Kubernetes scales up the respective nodes, pulls the images, and then runs these experiments. Typically, extract calibration data sets. If we use them for the conversion process, we convert the model, we evaluate the model, then we aggregate all the results of the different conversions and write a programmatically created report into 1TD. That gives then an overview of the effect of these changes over the conversion of the networks that we use for benchmarking. And when the CI pipeline's finished, our engineers in GitHub in the PR, they see a commit comment that links to the execution in Flyte. And when the author of the PR or the reviewers of the PR, they click on that execution link, they are presented with the workflow graph, for example, like this one here on the right. I grayed out what is written in these boxes, but imagine that each of these boxes here represent a Flyte workflow that performs one test conversion of a network with that experimental change. And then in the end, we aggregate all these results and create a programmatic report of the effect of these changes. So to summarize, what we want to happen is that we want to give our ML engineers tooling or a platform that allows them to quickly prototype and test changes in an automated manner. We do not want to put them in a situation where they have to manually provision infrastructure, SSH in there, then do some non-reproducible one-off experiments with a lot of hand-holding and lots of Jupyter notebooks. We don't want them to have to manage infrastructure manually, and we want them to be able to quickly get an overview of the effects of the changes they are proposing, so that the authors and the reviewers can make a data-driven decision whether the change is a good one or not a good one. And now the last part, I want to talk quickly about why we chose Flyte for the workflow orchestration part in our developer platform, or basically in this process. And for those of you who haven't used Flyte, let's imagine that we have a function called train, and that function, let's assume it trains a model. Obviously here we just return the smallest possible neural network in an untrained way, but let's imagine it trains a model. And to make this run in a Flyte cluster, what you do is that you decorate it with a task, and then in the task decorator, you describe how you want the infrastructure to look like for your experiments. And And what I want to show here is that if you do it this way, then the ML engineers can describe the infrastructure they want for this part of their experiments in Python. So they just say, for example, hey, the training logic in this function here needs 1 GPU and maybe 5 CPUs, 10 gigs of RAM. And then Flyte will make sure over Kubernetes to provision the infrastructure for this part of the experiment. And the engineers, they don't have to manually create VMs and they don't have to deal with YAML. They can write everything in Python, which of course for them makes it way easier to quickly implement an experimental change compared to having to modify some complicated build pipeline defined in YAML, for example. Another cool feature that makes Flyte really attractive for this task is that it has a powerful caching mechanism. So imagine that we make a very small tweak to like some small part in the conversion logic in our library. Then we probably don't have to calculate all tasks and all these workflows again. Maybe let's assume the changes maybe in this last part here. Would be great if we wouldn't have to do the first parts again, right? And in Flyte, you can simply activate caching, and then if nothing changes in these tasks here, then you immediately get the results back. That means that you have the results of your experiments faster, you can iterate more quickly, and of course you also save money because you don't have to calculate these results again here. Another thing that we really like, also one of the reasons why we chose Flyte, is that it makes multi-node, multi-GPU training very easy. So that's maybe less relevant in our conversion library, because you don't need that much compute to convert. But for the development of our perception stack, that's very relevant because the data sets in the automotive space are very large, and you want to crunch through the data more quickly than you could on a single node with a single GPU. But what I've seen in the past is people do that manually. The multi-node, multi-GPU training is that you have to create a bunch of machines. Then there are SSH scripts that install certain requirements on all of these machines. You have to copy the training code of all these machines and then get the IP address of the master node and set an environment variable for touch distributed on all the other nodes. And then on all of the nodes, you have to start the training function. Now that just makes it very complicated. And the nice thing in Flyte is you can just say task config equals to PyTorch or TensorFlow, or in this case, Elastic here. You say how many nodes you want, 16. Each of them gets 1 GPU. And then Flyte makes sure that the infrastructure here that infrastructure is provisioned and that the logic in this function here is run on 16 nodes with 1 GPU each. And we Recogni actually upstreamed this Elastic plugin here because we wanted to have a way to do what Torch Run does. So be able to do multi-GPU training when you develop locally, and then multi-node, multi-GPU training in the cloud. So when you set a node equals to 1 here and execute the workflow Python workflow.py, then we execute the task function 4 times in 4 processes here. So you see the output 4 times. And then once we're happy with the logic, then we set a node to a larger number. We send it into the cluster, and now we get 4 pods in the cluster with the resources that we define in the task decorator. And then in each of those pods now, we run 4 processes. So in total, we get 4 times 4 worker processes. So we do 4 times 4 multi-node, multi-GPU training. And the creation of the infrastructure is all abstracted away. You just define the logic that runs on every worker, and you define how many nodes and how many processes you want. And you can then run it locally when you set a node to 1. And then once you're happy, you increase the number of nodes and send it into the cluster, and everything kind of works automatically, which is super convenient. Last point that I want to highlight is that Flyte makes it very easy to leverage cheaper spot instances. So the ML engineers can set their task to be interruptible, and then the platform that we in the MLOps team configured will scale up nodes that are preemptible on Google Cloud, and the ML engineers implement their training and logic in a way that it regularly writes checkpoints into Flyte's so-called intra-task checkpointing mechanism. Then it doesn't matter if the cloud provider takes the machine away, because Flyte then knows, I can retry this task 5 times, and then on every retry, the training is continued from the recent checkpoint. And then on the last retry, Flyte switches to a non-preemptible machine to guarantee completion. And this way, we're able to leverage these cheaper machines and just save money doing so, which is really cool. Already reached the end and also the end of my time. I introduced what we do at Recogni. We develop inference systems for autonomous driving and in general autonomous mobility applications. Our inference systems use very little power but have a lot of compute and low latency. We do that using in a smart way, removing efficiencies in neural networks regarding over-parameterization and overly precise computation. And then I described how our ML teams develop a library to convert neural networks and how we in the ops team provide the ML teams with a platform that allows them to quickly prototype and experiment and only incorporate changes into their library that really make sense. And then I highlighted why we chose Flyte for the workflow orchestration part of our developer platform.
Saying thank you, Fabio. We're going to jump over to Arno, who's going to give us his last talk, and then we'll jump in for any final questions. Arno, whenever you're ready, take it away.
Sure. Yeah. Thank you very much for having me. I feel right at home, not only because I have a very similar slide as Fabio, but also because we actually made just about every mistake that David mentioned in his first talk. So know what he's talking about. So I'm from Blackshark. I'm the CTO there. Basically what we do is, we produce a 3D digital twin out of satellite imagery. Our most famous customer is Microsoft's Flight Simulator. And the idea of what we are doing is, we're taking some petabytes of satellite imagery, then we do our ML magic and some other data conflation, and out, so comes a 3D digital twin, or we're just using our magic for geospatial intelligence or whatever. So what we are doing is basically we are running models on planet scale data set, and of course we're running in all sorts of issues, right? And probably the most prominent are not only the costs, but also the model management, the data management, the scalability, the integration with all of the other moving parts, the monitoring, the tracing, and so on and so forth. And what I would like to do is I would like to just pick out some of these issues and talk about our experience when we were, growing from a small team to the state we're in now. And one of the key lessons is really this product mindset needs to permeate the entire company. So here is the more or less the same slide as Fabio showed. We're mostly talking about some of these requirements over there. And for me, it's all about the process that is inherent in this flywheel. So one of the lessons which are is basically probably not a surprise is, requirements change all of the time. And I'm not talking about the data drift or something else, but, your customer is saying A today, and they're requiring B tomorrow, and in a week they would like to have C. So all of this change needs to be part of your DNA, needs to be part of your processes. And actually there is a lot to learn from software engineers because they actually have a few decades more of experience, right? So this actually means that you should design your processes for change, because not doing so is very costly. And for change, I not only mean, okay, I receive a new data set or some small tweak here or there. The market changes, your requirements are going to change, your sales team suddenly has new requirements for you. All of this eventually leads to you needing to invent new stuff. So the faster you're able to do so, the better for you and your company. So this means design for reuse, not only of your processes and the steps in there, but also reuse data, because depending on if you're doing supervised or unsupervised learning, data, and especially labeled data, is really expensive, either because you're paying for the labeling yourself or you're buying it. And you should also try to reuse your models wherever possible. So as an example from change in our domain, we do not have the typical slow data drift, which you might see in e-commerce or anywhere else. It's more like, for us, it's maybe we're dealing with a new customer who has a different image provider. So this new satellite sensor has, different optics, has different spectral sensitivity, and so on and so forth. And so suddenly we need to fine-tune our models for this new sensor. Or, for example, post-processing by the image provider is changing. As an example, there is a process called ortho-rectification, where basically when a satellite looks at the Earth, all of the terrain, the ups and downs, need to be flattened out. And the way you do is you have a digital elevation model, and you use some geometry basically to flatten the image. And if the satellite image provider uses better improved processing or has an improved elevation model, something might suddenly look different. So the main question is, how well do your models transfer to these new requirements? Do you need to retrain? And the problem is, especially if you're dealing with another provider, suddenly your labels might no longer match. Because initially, when I started out in this field, I thought, satellite imagery is precise, but the truth is they might be off 10 meters or more. So if you have labels and suddenly your labels are off by 10 meters, it's no way to train your models. So actually, we invested into, auto-aligning images or adapting labels to different nadir angles, because a satellite, might look at the city from one angle, and the next time, in the next flyover, it might look from the other angle. And what this means is that high buildings actually move across the image faster than low buildings. So if you have labels and suddenly a different angle of the satellite, you need a way to, adapt your labels if you would like to reuse your data. And of course, as mentioned, for example, due to elevation models, your image might be warped in a different way. And so unwarping is something which we also do. For us, the lessons learned were basically, we're investing heavily in robust models. We know that training data in our case is expensive because labeling takes time and resources. And for example, using OSM, OpenStreetMap, might be a solution for some features, but not for all of them. And in addition, unfortunately, OpenStreetMap typically does not match the satellite imagery because they label footprints and not the roof. So this is something which you should keep in mind when you're setting up your MLOps workflow. Another area, of course, is, you're having all of sorts of metrics about training loss, accuracy, F1 scores, and so on and so forth. Basically, we're doing the same as we're doing this stuff all over the world. We have validation areas all over the world where we have ground truth, and all of our models basically run everywhere in different zonings, in different areas and regions. And then, we see the metrics if a model is good enough. Truth, of course, is that metrics only tell half of the story. So on the right side of the screen, you see one of our model failures where actually the model was doing very well, but in some areas, basically some of the neurons didn't fire, and we had a very different inference mask than in the rest of the image. And so if you're thinking about metrics, your metrics are not an end to themselves, but they actually stand in for some quality which you would like to measure, which you would like to quantify. And, some quality attributes are actually very hard to quantify, so it's hard to come up with a sensible metric. And some metrics might not be a very good proxy for the stuff you're actually caring for. And like on the right-hand side, sometimes islands of bad results might actually hide in otherwise good metrics. If your validation area is rather large, it might be that small pockets of bad results do not have that much of influence on a metric. So what do you do, right? You do some manual reviewing, but in our case, Earth is really large. So what do you do? Do you do heuristics? Do you guide your manual QA by another AI model, looking out for similar areas or for similar results? Do you do randomized tests, or do you just rely on the gut feeling of your engineers? In our history, basically, we used all 4 approaches, but for your problem and for your company, you really need to decide, are the metrics good enough, or, which is most often the case, should we also have a manual look at this? So the lessons learned is you should really design your metrics very carefully, but don't trust them blindly, and probably also invest in tooling for manual QA, either if in your domain you're able to buy a solution off the shelf, go for it. Otherwise, probably you need to develop it yourself. So switching to the next point, infrastructure costs. The first thing that typically comes to mind is it's all about compute, right? You're dealing with spot instances, GPU versus CPU tasks, tailoring, memory, number of cores, and basically what you're aiming for is high utilization. And as Fabio mentioned, this is an area where Flyte really shines, where your engineers, without much knowledge about the rest, are just able to specify exactly what they need, and Flyte takes the other care of the rest. One of our learnings was, you need to make sure that your workflow engine has the ability to do something like this. One of our learnings also was that, for example, storage might actually be expensive. Intermediate results, Fabio mentioned, if they are very large, as in our case, how long do you store them? When do you remove them? How often are you going to reuse them? So you need to have a policy. Also, you need to have an eye on your IO ops, because otherwise you're never getting this utilization. Your tasks start as containers, but the data has to be downloaded. And we redesigned actually some of our tasks for faster download, for less access to the disk, and so on. And what we also learned is when you do billions of blob writes, it's also actually really expensive, which in our case, for example, led to redesigning some of the workflows we use, where we eventually merged some of the tasks to a single task in order to avoid writing the intermediate results to blob storage. Another thing, and here I'm wearing my CTO hat, is process costs. You should have metrics for your processes. When you're a 5-person startup, probably this is overkill, but once you grow to a certain size and your organization reaches a certain maturity, you should really know how much effort you're putting in from the first idea for what you should do to the final deployment and operation. And ideally, this includes every email you send, every meeting you have, and so on and so forth. Also, it really helps if you develop an organizational knowledge of the risks which you usually encounter. For example, are you able to detect these features at all? And what you really should do is, profile your processes like you profile your code, identify the bottlenecks, and this is where you should invest your time. For us, for example, an example was, should we train, let's say we have a feature, I don't know, swimming pools. Should we train a model which is able to detect swimming pools all across the planet? Or should we have specialized models, let's say one for North America, one for Europe, one for Asia, and so on? So what are the trade-offs? What is the aggregate as a cost of development and also running this stuff in production? And you're only able to answer these questions if you have some metrics about your process. So the lessons learned: measure your process costs, ensure high utilization, and look out for stuff other than compute that might cost you. Another point which I would like to mention is integration. Again, in our case, basically we're going from image to 3D twin, but in between, we're adding a lot of other data, elevation models, land use, land cover, zoning, and so on. And for all of this, of course, we also need workflows, right? And here again, we're using Flyte, so we're not only using it for MLOps, we're also using it for other stuff, because using the same tool actually simplifies your infrastructure. And what is more important, it reuses skills of your engineers. You're not splitting up the brain pool onto different tools. And it also allows to reuse tasks in other codes. So the lesson we learned, the cognitive load is real. You need to minimize it for the benefit of your engineers, which in turn also means keep your systems as simple as possible, unify and try not to over-engineer your solution. So far, I've only been talking about ML engineers and software engineers and so on, but actually you probably also have domain experts, either as external or internal users. And for domain experts, unfortunately, most of the time, your tools and your development environments are not as user-friendly. And if you want your domain experts to, move forward at speed, probably what you should do is, make an easy point-and-click interface. Like, for example, here, which we termed World Operator, is basically a nice point-and-click front end for Flyte workflows, which are running in the backend. And, for them, it's totally abstracted for what is actually happening in the background, how many, let's say 100 machines we're launching in the background to do a fast computation of this task. And another thing which you might have heard in one of our recent announcements is we're having, for example, a tool which allows rapid prototyping of machine learning models. Basically, you scribble on the left-hand side, like using crayons in kindergarten, and every second or other second, the inference mask on the right-hand side shows you what the model identifies, which immediately gives you feedback for false positives, false negatives, and then you scribble some more. And within minutes, hours, you're able to train a model with very high accuracy. For production level, probably you need 2 or 3 days. But if you're using it for rapid prototyping, like, are we able to even identify this feature? Then this is the tool of our choice, which we have been using internally for years and which we're now making public. The lessons learned here is your domain experts are not your developers, so you probably need to build tools for your experts as well. So summing up, training data is expensive. You should have a solution there. Design for reuse at every level of your stack and your processes. Don't trust your metrics. Measure your costs. And as we learned the hard way, complex systems are hard to handle, and don't forget about your domain experts and users. So in a nutshell, this is the hard lessons learned from running AI models at scale.
That was awesome. Fantastic. And great timing. I think I'm going to bring everybody back in. For David, we had a quick question actually, which was, do you have any other examples of computer vision heavy startups kind of in the automotive world that are using Flyte in production?
Yeah, I can put here the link to the public adopters list. It's not an extensive list by any means, but some of the orgs there, their use case include computer vision. That is the case for Wooden Planet. They are in the business unit inside Toyota, helping design next generation self-driving vehicles. They are Flyte users. Also, MethaneSat. MethaneSat is designed to be the most advanced methane tracking satellite in space. So finding methane emission sources throughout the planet and trying to tackle the climate change challenge. And they are Flyte users. And in the also Pachama, they also use satellite data to estimate carbon credits. And we have other users in the automotive space that we cannot mention publicly, but you'll be surprised. So hopefully in the future we can mention them publicly. But yeah, this is a short list.
Do you think there's something about Flyte that is particularly attractive to that industry, or do you think it just happened to catch on and Flyte would be kind of generically usable as a workflow engine?
Yeah, probably Fabio or Arno can answer better that question, but yeah, it has.
I personally would say the latter. It's generally really handy for any type of machine learning and deep learning. And since a lot of that is done in autonomous driving, it's great to apply there, but you can apply it in any other ML field as well. I would say there's nothing that makes it special for autonomous driving.
Arno, same from your end?
Yeah, basically the same sentiment. I mean, for us, one of the prime reasons why we chose Flyte is because you're able to customize it. You know, you're able to have your own data types, your own stuff and so on. And so for us, this was one of the main reasons, actually.
Very cool. Very cool. Well, thank you all so much for jumping on and presenting these use cases. They were really interesting. And a huge thank you to Union, who is sponsoring this meetup and helping the community out. It really wouldn't be possible without help from our sponsor. So we certainly appreciate that. And for any questions, I think people know how to get in touch with all three of you. We'll include all of your contact information and companies in the descriptions when we ship out these videos. But thanks so much. I think we're at time. Yeah, have a great rest of your day.
Okay, thank you very much.
Thanks for having us.